This is from 9.2, number 46, and once again, I'm going to go quickly through the state, the conditions, and the conclusion step, and spend a little more time on the computations. The scenario here is that P represents the population proportion of first-year students at a particular university who think being very well off is important. And there was a survey of first-year college students in a national survey that said 73% of first-year college students believe that being very well off financially is important. So there was a simple random sample of 200 in this particular university, and 132 of them agreed with that statement. So the question is, do the proportion of first-year students at this university who think being very well off is important differ from the national value 7.73? So we're going to use a not equal to, so this is known as a two-sided hypothesis test. The simple random sample of 200 we assume that the number of first-year students is greater than 2,000. So that's the same thing as saying we think 200 is less than 10% of the population. We think the population is greater than 10%, is greater than, 10 times the number of students. We have the NP and NQ, both validated. Remember that the P is the P used in the null hypothesis. So we can proceed with a one proportion Z test. So here's our sample statistic. 132 out of 200 is 0.66. Okay, so we calculate our test statistic, but in this case, it is a two-sided test. So we are not only concerned with the area that's beyond 2.23 standard deviations below the mean, we also want to know the area under the curve that is 2.23 standard deviations above the mean. So our p-value encompasses both tails. All right, so how do you go about calculating the p-value? Well, one way we can do the normal CDF, and notice I used the 0.66 and the 0.73 and the standard deviation, or I could have also done normal CDF negative infinity negative 2.2301, and I would have gotten the same thing. Notice then I did it using the test on the calculator. Let's run through that test on the calculator one more time just to make sure you remember how to do that. So doing this is from my previous example, so let me clear this off, clear the history. All right, so we do menu, statistics, stat tests, one proportion Z test. If I go back and look at my sample, it was 132 over 200. So this was, the null hypothesis was 0.73, this was 132 over 200, and we have a not equal to now. So when we look at this, there's the z-score that I got before, but my p-value is different. If we go back and look at the p-value is twice as much as what I did with the normal CDF, because the normal CDF is just saying I want to know what the area of the tail is when I'm less than the 2.23 standard deviations below the mean, but it didn't include the one above. So we have to double this value. So if I take this value times 2, which is what I did in this line, I get the same value as I find in the test. So the test does the doubling automatically for you. Now this is a small p-value, so our conclusion then ends up being, since the p-value of 0.0257 is less than the alpha value of 0.05, I reject the null hypothesis. There is convincing evidence that the proportion of first-year students at this university who think being very well off is important is different than 73%. Well, just saying it's different doesn't really tell us a whole lot. So sometimes it's useful to do a confidence interval to give us more information about what that population proportion truly is. A two-tailed test when alpha is 5%, in other words, my rejection region is in both tails 5% together, would correspond to a 95% confidence interval. So if I do a 95% confidence interval with this information, I get these endpoints for my confidence interval. And so we can also add to this. Now this isn't part of the hypothesis test, it's just additional information. We could add that we are 95% confident that the true proportion of students who think being well off is very important is between 59% and 72.5%. So we're almost not rejecting the null hypothesis with this confidence interval, but we're able to do that. Now, recognize that a confidence interval is using a different standard deviation. It's a standard deviation based on the sample proportion rather than based on the population proportion. So it's a little different. And so that's why there's the discrepancy where that 73% is almost in the interval, where it wasn't that close here. The 0.257, the 2.57% is not all that close to 5% here. Once again, make sure that you're able to use the calculator or the table or by hand to calculate the p-value and the test statistic. Those are the two important values you need to show in the do step.